Now we return to Africa, Arabia. So we're going to look at the Red Sea, which is another one of these sites where continental rifting is transitioning to seafloor spreading at ultra slow rates. So the spreading rates are comparable to the Southwest Indian Ridge, quite slow. It's interesting. It's a little different to the Gulf of Aden, where you see the bathymetry is deeper, and that's reflecting the great thicknesses of sediment in here. So we've been interested in how do those sediments affect the magnetic signature of breakup, or another way to put it, what can you infer from the magnetics about the process? I'm showing work done mainly by two PhD students, Oki and Wen. Wen's gone back to China. These are their two articles. So mainly their work. So in general, just to revise this, we're interested in how continental breakup proceeds. This is a model by John Armitage and others. Proceeds by necking the lithosphere. That leads the mantle to rise up and melt. It would be nice to have data sets that showed when this molten material broke through to form new crust in relationship to the mechanical deformation. In most places of the world, it's quite difficult to study. This is a compilation of ocean continent boundaries by Graham Eagle for the Gulf of Mexico, which you would think is quite well studied. But different research groups or different researchers have placed the continent ocean boundaries in quite different locations, sometimes even based on the same data sets. So locating this boundary can be difficult in mature margins. It suggests it's quite a difficult thing to study. So just to revise our, I guess this is undergraduate level science, at a mid-ocean ridge where you get melting in the Earth's mantle, that produces molten rock which erupts at the seabed. Where the lavas are chilled by seawater, magnetic minerals are formed, but with very, very small grain sizes like titanomagnetite, and they record the Earth's geomagnetic field quite well. So when you tow a magnetometer across a ridge, you detect the successive positive and negative polarity of the seabed produced by the seafloor spreading process. A key here is that the lavas are quenched fairly quickly, and maybe the dikes are also fairly quickly cooled. But let's look at some very old ideas about the Red Sea. So these are cartoons produced by Ron Girdler and Bob Whitmarsh back in the 1970s. This is what the Red Sea was thought of at the time, the structure. I think we would change this somewhat, but still, possibly during the Miocene, the Red Sea was probably floored almost totally by evaporites. And when you had seafloor spreading occurring, somehow it occurred underneath the evaporites. At the modern day, you see seafloor spreading occurring and basalts at the seabed in a number of places. So there is normal seafloor spreading occurring like here, and the evaporites are actually forming these roughly dipping strata to the side. It's been, because it's so difficult to collect high quality data in the Red Sea, and the thick evaporites cause problems. They make it very difficult to image basement. There's been a big controversy over what actually underlies the Red Sea. We teamed up with Izeldin, who's a senior Sudanese scientist who studied the Red Sea for his PhD a long time ago. Zeldin had access to some deep seismic reflection lines run along these red lines here, crossing this is the central red part of the Red Sea. These were collected with a 2 kilometer or so long streamer, so the data weren't so bad. Unfortunately, the digital data are lost. We've only got access to paper copies. But what we've done, or Wen has done, is taken the interpreted basement from those seismic sections that Zeldin created, depth converted them. And so these are profiles corresponding to these profiles over here. And you'll see, sorry, he's also verified these basement depths by magnetic source depth calculations. And you see these big clouds of circles, but they do very roughly corroborate the interpretations. If you look, the cloud is limited roughly by the basement reflection. So the basement underneath the central Red Sea is actually a ridge. This is not what you would expect from a continental rift. This shape is very much as you would expect for a mid-ocean ridge, perhaps near a hotspot, since the spreading rate is ultra slow. So that's our interpretation of the basement reflections. It's the basement is quite rugged, so but that's in keeping with what we see at other ultra slow spreading ridges, and it's what we would expect with some hotspot influence. I'm just summarizing a lot of information, but essentially Wen has found that the Bugey gravity anomalies are quite strongly correlated with the top of basement, but they're not correlated nearer to the coast. So although the basement may come up to the coast, Bugey anomalies are flat, and this suggests we have probably continental crust underneath these areas. And this transition from continental to ocean, we would put where the basement minimum occurs. There are also some seismic refraction data which also corroborate this, and the magnetic anomalies, which I'll now talk through. So these were collected by aircraft, aeromagnetic anomalies, in the 1970s, and Zeldin also used these for his PhD. They've been reduced to the pole by Ed Stewart, who has worked for the Saudi Geological Survey. There's quite a good density of lines, and they've been well navigated with a local radar system, and they've been reduced with a base station readings. They're quite reasonably good data. What you should see fairly obviously, there's this axial anomaly here, and there are parallel and symmetrical anomalies either side of it. So down here, this is clearly a seafloor spreading anomaly sequence. In here, it's a bit more confused, but this is not unexpected because here the ridge is oblique. Like in the Gulf of Aden, we expect a series of spreading centers that are offset from each other. And Roger Searle did some modeling to explain why the anomalies would be complicated in here. That's fair enough. But what's hasn't been perhaps so obvious is that there are also anomalies that are off axis that are roughly parallel, maybe not so striking. So this pair here you might associate. So could they be of interest? So what Oki has done is he's taken the aeromagnetic anomalies and he's inverted them for magnetization of the upper crust, assuming it's all the source layer is 500 meters thick. So he's used the basement from the reflection data for this. When you do this, you remove some of the depth to source effects, so we can compare the amplitudes of the anomalies better. We see the amplitudes are quite large off axis, so if the anomalies are low apparently in magnetic data, that's because the source is very deep And when we reverse that effect, they're not so low. The anomalies around the axis of the Red Sea have quite reasonable high frequencies, as you would expect for seafloor spreading anomalies. Off axis, going towards the coast, they get smoother. There's this interesting large anomaly or magnetization peak at about 60 to 80 kilometers from the axis. And it's roughly symmetrical. You can see it on some of the lines, not all, but some. So here again, there's a symmetrical pair of anomalies. So Oakey's focused on that a little with some quite simple modeling where he's taken the Earth's geomagnetic field, used that to produce a magnetization model in which the magnetization decays. This is what we observe in some of our, in our data, we see apparent decay, I should say.
You're at 10 minutes now.
Okay. He has filtered the data to represent the geological process. So you get eruptions of lavas in the spreading center, for example. So you expect them to cover a finite area, and other processes which tend to smooth out the anomalies. If he uses a 12-kilometer filter, given by the red line, you see the frequency content of the data is actually not too different from the model. It's actually not too different from the data. It becomes harder to model the off-axis anomalies. And indeed, this one we call Cron 5, it's so broad that you can't easily model it by this method. If you use a long wavelength model, you end up destroying this anomaly because the negative magnetizations cancel the positive magnetizations. So it appears that this is a feature that has a lot of magnetization, if you like, more than you would expect from seafloor spreading. Could it be a lot of intrusions at the time of breakup, which is our question? We can't prove this because we don't have quality magnetic data or seismic data to look at it. Oakey has also taken a grid of magnetizations and he's computed east to west gradients through the grid. And we do this to boost the high frequencies. And when you do that, there is this quite striking change from very high frequencies at the axis to lower frequencies. And if you look, or if you agree with our stars, where we've marked our transitions, it gets narrower to the north, which is also quite interesting. What he's done on the right is he's made a grid of magnetizations by applying plate rotations and the geomagnetic timescale. And he's also worked out this gradient. And you see in here, the stripiness, if you like, and the frequency is roughly the same here. But then here, of course, we don't see that in the data. So something changes here. It's really quite striking. So this is our wild speculation, if you like, going back to the end of the Miocene, or near the end of the Miocene. In separate work, we've tried reconstructing the depositional level of the top of the evaporites, and we think it lay much shallower at the end of the Miocene, maybe only 200 meters below modern sea level. It's gone down since then because of thermal subsidence and the flowage towards the spreading center. So you have a broad-based deflation. But going back into the Miocene, it would have been much higher. And so it seems quite possible that it would have flown, it would have, because it's quite weak, it would have covered the whole of the spreading center. And at that time, seafloor spreading occurred underneath the evaporites and the halite and the other salts. We don't know what happened, but perhaps if you had intrusions, firstly, you'd expect slower cooling. So you would tend to get lower magnetizations than normal, which is what we do see. And maybe sills and so on would explain the long wavelength. Towards the present day, we've had more seafloor spreading, so the whole system's been opening. But at the same time, the evaporites have been flowing towards the spreading center. But this flowage has occurred slower than the seafloor spreading at the deeps. And so the deeps have opened up. And that opening of the deeps and cooling of lavas at the seabed by seawater possibly started at 5 million years. And that's when we started to get these very high frequency anomalies. So it suggests, so the salt potentially has produced this interesting transition. So the ocean continent boundary may be here, but there's another transition a bit later as the sedimentary system has changed as well, with this opening of these deeps. And that's all I have to say. I've tried to keep it short.
Excellent. Thank you, Neil, for a very interesting talk. Any questions? Again, put your hand up or put something in the chat. In the interim, oh, Derek's got a question. Derek?
Thanks, Neil, for an interesting talk. I've got a few questions about this slide, actually. I was wondering why, I have a few questions that you actually answered on the slide, but I have a few more. Why does the flow of the evaporites not keep up with the extension more recently? Like, what's changed? Why is either the flow rate dropped or the extension rate increased?
I think it's always been slow. Well, firstly, I should say I don't know really. When I first worried about this, I was worried about halides because salt flows in Iran made of halite flow very fast. So why aren't these flowing fast? And it seems the reason is there are a lot of layered evaporites which are fairly rigid because of their anhydrite content. So it's not pure halite. So they don't seem to, they do flow into the axis in some places where we have the intertrough zones, but not where we have the deep. So they seem to be just sufficiently rigid that they don't completely swamp the axis. It's difficult, we can't predict. We can look at some published seismic data which show reflectivity, so we get an idea of how much of this layered evaporite there is. Of course, we haven't got cores or anything to do anymore.
Okay, thanks.
Yeah. I see we also have a question from Marta Perez-Gassini, who I didn't notice was here. Marta?
Yes, hi. Thanks a lot for the interesting talk. I was wondering, what's your estimate of the depth of breakup?
Depth of breakup?
So the depth at which breakup occurs. So when
we don't have we don't have good deep seismic data. If you mean very deep, I mean there is some seismic refraction data, but we're questioning that. We're trying to do some for misunderstood.
Yeah, so the depth at which breakup occurs. So, I mean, do you have an idea of if the basement was very deep when breakup occurred, or it was very shallow?
Okay, it probably was quite deep because it would have been filled with evaporites. So they isostatically loaded the continental rift as well, I think. Could I put, I don't think I could put a number on it exactly. I could try to reverse the cooling, which I've done with the evaporites. So it will have been shallower than today, and it will have deepened with lithospheric cooling. But it would be deeper than a normal margin because of the loading by these evaporites.
Okay. Thank you.
Oh.
Okay, are there any last questions?
This is Brian Taylor. Neil, in plan view, where is your continent ocean boundary in this cartoon relative to those off-axis anomalies?
Well, if I go back, well, in here, I would say it's somewhere like in here. So you don't see anything in this map. In here, I don't know, it could be in here. You do see evidence of these long things, which could be dikes, or maybe this is a pair. So this could be oceanic spreading, maybe in here. So it would be, well, this is the anomaly I've been talking about. Did I include the gravity? The gravity anomalies, it would be about here.
Thank you.
Yeah.
Just one last question. Might there be any mantle exhumation in the Red Sea, or is that crazy talk?
That's crazy talk. Yes. No, it's a good question. I have been asked that. Nobody's dredged mantle rocks. We've got, I think, one gabbro, but no mantle rocks. Yeah, it's like there's been no serpentinites found. It's difficult to say, really. We see roughly symmetrical ridge here. There are very diverse opinions of the northern Red Sea, so that might be more of a possibility. So I should give the answer is I don't know, I suppose I should say. That's the honest answer.
Safest answer as well.
Yeah.